My name is Nick Cutler, and I'm going to talk about the preservation of the Tephra deposit produced during the 1980 eruption of Mount St Helens. When we started the project, we wanted to know, firstly, how reliable are Tephra layers as records of past volcanic eruptions, and what factors are significant in the preservation of Tephra. We used the 1980 Tephra layer as a case study to address these questions. This project was a team effort carried out in collaboration with Andy Dugmore, Anthony Newton and Polly Thompson from the University of Edinburgh, and Richard Streeter from the University of St Andrews. Bridget Jensen and Matt Bolton from the University of Alberta and Sam Engwell from the British Geological Survey also made invaluable contributions. Tephra layers are obviously tremendously useful things. Their use as chronostratigraphic mark horizons is well established and has expanded dramatically with the mapping of cryptotephras. They're also vital resources for volcanological reconstruction, giving us insight into magma geochemistry, eruptive behaviour, and the extent, frequency, and severity of volcanogenic impacts. Inferences made from Tephra layers are premised on the assumption that the preserved Tephra is representative of the initial deposit, but a lot can happen post-deposition, and this may obscure the signal carried by the Tephra layer. The cartoon on the slide summarises some of the factors that might affect the preservation of a terrestrial Tephra layer. Immediately after an explosive eruption, Tephra mantles the landscape, and that's shown on the left-hand side of the slide here. But while the Tephra is on the surface, it's exposed to reworking by wind, water, and slope processes. The deposit is likely to be compacted. It's also subject to biological transformation, for example, burial by leaf litter. Eventually, the Tephra may be incorporated into the soil profile as a Tephra layer, but a buried layer might still undergo chemical transformation and disruption by soil organisms. Overall, in terrestrial settings, we might expect a thinning of the deposit due to erosive losses and compaction, increased variability in thickness, as some areas are eroded, some are sheltered, and some receive remobilized Tephra, and the preferential loss of finer fractions. These processes reduce our ability to make accurate volcanological reconstructions, but they aren't well understood. The ideal way to study Tephra layer formation is to observe the process directly in real time, but this is obviously challenging. We took an alternative approach. We decided to resurvey a well-known Tephra deposit, comparing measurements taken shortly after the eruption with contemporary observations. That way, we could quantify the transformation of the initial deposit. We aim to estimate the fallout volume with a mathematical technique applied to both the original measurements and our field observations. We also wanted to assess how the Tephra layer varied in space and whether we could generalize about the kinds of environments that are good for Tephra layer preservation. We focused our study on Mount St Helens. Mount St Helens is the perfect location for this kind of project for three main reasons. Firstly, the 1980 eruption spread Tephra over thousands of square kilometers, and most of the fallout was on land. Tephra was deposited on contrasting vegetation types, allowing us to consider the impact of land cover on Tephra layer taphonomy. Secondly, although the eruption is recent enough for good records to exist, sufficient time has elapsed for taphonomic processes to play out. Thirdly, and I think most importantly, there are excellent contemporary records of the initial Tephra deposit. The USGS commenced a survey of the fallout within days of the eruption, making over 200 measurements of the deposit thickness and collecting fresh samples for grain size analysis. In addition to possessing properties characteristic of all Tephra deposits, that is, thinning and fining with distance, the 1980 fallout had two distinctive features that are relevant to our study. Firstly, there was a secondary thickening of the deposit centered on the town of Ritzville, and that's highlighted on the original isopach map here on the right-hand side of the slide. Secondly, the grain size distributions in the proximal deposit exhibited marked bimodality. Our fieldwork tried to emulate a survey of an unknown Tephra layer, although we did cheat and used isopach maps to locate areas where we were likely to find Tephra. We set out to obtain lots of measurements of Tephra layer thickness from across the fallout zone. We wanted the measurements to be evenly spaced and to encompass both proximal and distal areas. We targeted locally flat areas of natural vegetation cover. Much of central and eastern Washington state is used for intensive agriculture, so we targeted nature reserves in these areas to maximize our chance of finding undisturbed Tephra. We weren't able to exactly replicate the original USGS survey, as their measurements were made in a pre-GPS era, and many were from locations that would not allow preservation, so for example, paved roads or parked cars. Because we could not replicate the 1980 measurements, we relied on interpolation to estimate the initial tephra thickness at our sampling locations. In total, we surveyed tephra thickness in 86 locations, ranging from 13 to over 600 kilometers from Mount St Helens, and that's indicated by the red dots on the slide. We also collected proximal and distal samples for grain size analysis. So what did we find? Well, firstly, let's look at tephra thickness. Much to our surprise, we found tephra from the 1980 eruption pretty much everywhere we looked, even in areas where the initial deposit would have been relatively thin. The thickness of the layer we observed closely resembled the thickness of the initial deposit. This was particularly clear on sites that were on the main axis of the eruption plume. The figure on the slide compares the 1980 survey along the plume axis, shown here with black points, with our measurements shown as red points. In both cases, the exponential decrease in tephra thickness is clear, as is the secondary thickening around Ritzville, approximately 300 kilometers from Mount St Helens. This figure compares our field measurements to interpolated initial thickness. In proximal locations, shown here as red points, tephra layer thickness matched or exceeded the interpolated 1980 measurements. In more distal locations, shown with this little cluster of blue points, the tephra layer was generally somewhat thinner than the initial deposit, but still within 25% of the 1980 value. Around the margins of the fallout zone, the tephra began to disappear from areas where the initial deposit was less than 5 to 8 millimeters thick. Our suspicion is that the deposits less than or equal to this range are not reliably preserved as visible tephra layers, but we'd have to conduct further studies to be confident about this finding. Layer thickness may alter without the loss or addition of tephra. For example, fresh tephra deposits may deflate, or they may be gradually supplemented with soil particles as they're buried. To investigate this, we also calculated mass loading at a selection of sites and compared it to measurements made in the 1980s. The figure on the left-hand side of the slide shows mass loading along a transect line perpendicular to the main plume axis, about 55 kilometers from Mount St Helens, and that's shown in plan on the right-hand side. Just as with the thickness measurements, the mass loading figures were similar to those observed in 1980. So you can make the comparison with the blue isomap lines on the figure on the right-hand side. Mass loading was highest near the plume axis and decreased towards the margins in a predictable way. The USGS recorded a clear stratigraphy in proximal tephra deposits, and they related the units they observed to phases of the eruption. The summary is shown on the right-hand side of the slide. We also observed distinct stratigraphic units in the proximal tephra layer. The image on the slide is from a forested site approximately 50 kilometers from Mount St Helens. It's typical of the tephra layer in this location. The tephra is buried under a few centimeters of organic matter. And note on the photograph how sharp the upper and lower contacts of the layer are. We identified 3 strata which map neatly onto the units A, B, and C in the USGS schema. In 1980, the proximal tephra deposit had a bimodal grain size distribution with a coarse peak and a more muted hump at around 6.5. This is shown in panel A on the figure on the left-hand side. The equivalent distributions from distal locations were finer and unimodal. That's shown on panel C. Our proximal samples were also bimodal. The peaks are in slightly different locations, but that's probably because our samples were about 15 kilometers further away from Mount St Helens. Our distal samples were fine and unimodal, like those from 1980, but they were truncated at the coarser end of the scale. We think this was due to the retention of coarse particles in the biocrust that capped the tephra layer. And you can see the biocrust on the image on the right-hand side as this kind of orangey layer on the top of the soil. The biocrust is composed of a layer of moss and lichens that had formed directly on top of the tephra. Contemporary accounts suggest that biological colonization commenced within days of the eruption and probably helped to stabilize the fine deposit. Finally, our reconstruction of the fallout. Sam Emwell helped us to reconstruct the fallout volume using both the 1980 measurements and the results from our survey. We expected the volume estimate from our measurements to be lower than the figure from the 1980 figures due to erosion losses. Sam deployed an objective mathematical technique termed cubic B-spline interpolation. When applied to the 1980 measurements, the technique produced an isopach map similar to the original hand-drawn version, which is shown on the top panel with orange isopach lines. The isopach map produced from our measurements, which is shown in the bottom left panel with blue isopach lines, reproduced the main features of the original deposit, for example, thinning with distance from Mount St Helens and away from the plume axis, with secondary thickening around Ritzville. But there were peculiar islands of tephra around the margins of the fallout zone. To our surprise, when the two estimates were compared, the volume derived from our measurements significantly exceeded the volume calculated from the 1980 figures. Our modelling exercise illustrates the importance of sampling strategy in the reconstruction of tephra deposits. Even with dozens of data points and good preservation, volume estimates can be inaccurate, particularly if there are large gaps in the sampling grid. We had to include lots of zero values around the perimeter of the fallout to constrain the model, powerfully emphasising the importance of null results in tephra surveys. So those are our findings. What do they mean? What are the implications of our results? Our work shows that terrestrial tephra layers can faithfully capture the characteristics of the deposit from which they originated, which is obviously a relief. Contrary to our expectations, we did not see much loss of thickness, nor did we observe systematic changes in mass loading, stratigraphy, or grain size distribution. Our findings suggest that certain conditions facilitate preservation of tephra. Vegetation cover at the time of deposition can play an important role in sheltering and stabilizing fresh tephra deposits. Our results also show how tricky the reconstruction of volcanic eruptions can be. Automated isopach modeling is sensitive to sample location. Null results, although tedious to record, are crucial for bounding deposits. Our work has shown how complex tephra toponymy is. We liken the preservation of tephra layers to Hans Jenny's venerable equation of soil formation, which is shown on the top right of the slide. That is to say, the state of a tephra layer is a function of climate, biology, topography, parent material, and time. Tephra exposed on the surface is obviously vulnerable to transformation, and we suspect this vulnerability decreases over time as the tephra is buried. We tried to illustrate that with this conceptual model on the left-hand side of the slide. Early changes, erosion, sorting, physical weathering, could be followed by bioturbation, both at the surface and in the soil profile, hydrological and geochemical alteration. The impacts of processes that transform tephra layers will vary in time and space. Unpicking them is challenging. Natural experiments based on other tephra layers could be useful, but we may be reaching the limits of what we can discover with this approach. Because of this, we're going to concentrate future research on replicated experiments in which tephra is applied to outdoor plots and key parameters, for example, layer thickness and grain size distribution, are repeatedly measured over an extended period. We are reliably informed that stores of tephra from the 1980 eruption exist in a warehouse in Pullman, illustrated on the right-hand side of the slide here, a bit like Raiders of the Lost Ark. We'd be delighted to participate in collaborative efforts to liberate this material via experimental plots. So that's the end of the presentation. Thank you very much for listening. As I said at the outset, this research is a group effort conducted over several years. We'd like to thank our funders, the Royal Geographical Society, General Research Association, and Newcastle University. We'd also like to thank the people listed on the slide for their assistance, guidance, and insight. Thank you.